large extent is similar to a talk I gave in Europe just before the COVID pandemic. It's a bit different because in the course of going through my slides, I really didn't remember what I talked to, so I had to make it a bit more pedagogic. So anyhow, here we go. Let me start my own watch here on my computer, if I can. Okay, 25 minutes from now. So first of all, some recognition of the people who've done the work. So we have up here, we have Ignacio to the top left, and then we have Mikael Delcy, who now has a position in Stockholm at KTH. And then we have my dear friend Sørensen, who did most of the coding. And then we have Myron, who was a part of this project also, which was funded by the Carl Trigger Foundation, Knut and Alice Wallenberg's Foundation through the Codex project, and also the Swedish Research Council. Before I proceed, I would also like to make it clear that the work we have done on this is not unique. Quite a number of other groups have been doing similar work. And those that sort of sticks out that one should mention here is the work by Tromsø's group in France and the group by Christoph Jacob in Germany. So if you find this interesting afterwards, don't just look at our papers, but also look at the papers by Trond and Christoph. So the presentation today, I will try to give you a motivation why we did this and the background from the problem. And we're going to talk about origin dependence computing oscillator strength. We're going to dwell a bit on the truncation errors that one typically have during computing oscillator strengths. One thinks that one can do smart truncations, but that's really not the case. And then finally, I hope to end up with telling you how to do these integrations when you're doing X-ray spectroscopy. Typically, what I'm going to talk about here today will force you to do new sets of integrals for each transition you're studying. So I was approached a few years ago by a friend that wanted to do calculations of the spectrum of this molecule. And she also had this spectra. And I think she was using cos PT2 probably to compute these nice transitions and more or less nailed the transitions in the spectra. But what worried her was that intensities were completely off. So to the left, you have the column with the intensities. And on your right, you have the oscillator strengths computed in the length gauge or as a transition dipole moment. But to the most right, it also in the velocity representation. And here we see that sort of the intensities of the most strongly intense transition change when you go from one representation to another representation. And that was something I sort of anticipated because at the time she asked me about this, we were working on an implementation which was completely origin independent. So where is the origin? If we're looking at molecular systems with a single transition metal, most of the time the origin really doesn't matter. And also we tend to use, when we compute oscillator strength, the dipole approximation. And in that respect, we assume that the wavelength of the incoming photon is much larger than the molecule. But what happens when we have high energy photons, as we would have in, let's say we're doing X-ray spectroscopy, is the dipole approximation really something to trust? So we looked at this we stepped back in theory, took away as much as possible of the approximation, and what we start with is the semi-classical light-matter interaction equation and use that as a time-dependent perturbation. And here in this equation, we have the vector potential represented of A here. We have the momentum operator. We have a quadratic term in the vector field. We have one term here, which is due to the magnetic field coupling to the spin of the electrons. And if we use standard representations, these three different terms are replaced with these exponential expressions, which have a argument which is complex. And that's probably why most people try to stay off this. If we proceed, the oscillator strength is computed as follows. You have a polarization vector describing the polarization of the light, and you have a transition moment that has to be computed. And you take the norm of this product here, which in a product, which in itself can be a complex number. The transition moments are computed as follows here. The transition moment between states 0 and n. We have now this here, which contains all these different terms. And usually, as we proceed, we tend to ignore the spin contribution because that's usually very small. Actually, I don't know any case yet where it makes a significant difference. And also for the exponential expression with the complex argument, we go and do a Taylor expansion and we truncate that. So here I'm taking this exponential expression here and I'm replacing that with a standard Taylor expansion. And if we now start to truncate here, if we use the first term, we're going to see that the only thing surviving inside this integral is this term here, the polarization vector projected on the momentum. And actually what we call the dipole approximation honestly should be the moment representation. But there is a commutator that allows us to translate from one to the other in the case we would have an exact wave function, which we don't. Never mind, we'll come back to that. So what we proceed now is to compute this oscillator strength. And the first thing we realize is that we need, if we have unpolarized light, we have to polarize over the two different angles of the light. And if it's truly unpolarized, the polarization direction could be in any direction perpendicular to the k vector. So we have to integrate all possible directions. And what comes out is that essentially we need two representative polarizations vectors, epsilon1 and epsilon2, and we're projecting the transition moment on that plane. So actually we only need a transition moment on the polarization plane. The third component, which is in the direction of the k vector, is not needed. So now we have taken care of that, but then we have that the light is coming in towards the molecule from all kinds of directions. And if we want to compute the isotropic value, we now have to integrate over all possible directions the light coming in. In our implementation, we have solved that by a numerical integration over solid angles using a Lebedev angle. integration over solid angles. And because of symmetry, we only need half of the grid points, because whether the light comes in this way or in the same way but in a different direction really doesn't matter. To proceed these matrix elements over the time-dependent perturbation is actually transition moment densities times integrals, and these integrals, u of AB, typically looks like this. So depending on what I set these to, I can manipulate the three contributions such that it essentially all are integral of this type. And such an integral, if we're using Cartesian Gaussians, factors out different Gaussian components. Now this looks nasty because of the imaginary component here, but if we start to use the Gaussian product theorem and dwell a bit, this essentially looks like an ordinary Hermite-Gauss integral. However, the devil is hidden here in the Q, because the Q is actually a complex coordinate. It's the ordinary P coordinate plus this imaginary component. So that renders our integral to be an integral which runs in complex space. But it's essentially a path integral. So we can decide that we sort of, let's say we're starting here with minus this. We move perpendicular to the real axis, just moving in the complex plane in until we get to the real axis. Then we move all the way from minus the square root of e theta s all the way to the other side of the coordinate system. And eventually we move out in the complex plane. It just happens to be that if you look at this, the first and the third integral is 0. So at the end of the day, we're ending up with something that looks like this, which is an ordinary Hermite-Gauss quadrature. The only difference is our polynomials here could have complex coefficients. Apart from that, everything is very trivial, and you can code this up in a very nice and simple way if you have a code that already does Hermite-Gauss. You could also achieve the same thing by doing a modified McMurtry-Davison scheme, which is a bit more elaborate. So now let's discuss the origin dependence a bit, and I will do it from 3 different perspectives. One way is to look at the transition moment as it's defined and see that the total transition dipole moment, if I move the origin, I'm getting a complex factor, which is the k vector times the displacement vector. And I now have here the transition moment of the origin. Another perspective, we're going to look through these in some detail, is that I have, here I have the dipole approximation in momentum representation. And if I'm now doing the dipole approximation, or alternatively, so I have it in a momentum representation here, the same thing in the dipole approximation. We're going to look and see what happens to those. And then we can look at the transition moments to different orders and see how they transform into each other and what kind of consequences that have. So let's start with the first one, where I'm saying that this transition moment has this complex factor in front of it. And if we expand it the way Euler would do in a cosine and a sine part, we see that as A increases, this prefactors can potentially shift the real component of the transition moment into the imaginary and vice versa. And an important thing here is to understand how fast does this happen. And I'm writing here that if the displacement vector on projected on the k vector is equal to pi half or a multiple of that, we have made a complete change of the real and imaginary component. Now, what does that translate to? It translates to, like in UV, a displacement would have to be 500 to 2000 angstroms. No big deal. Whereas if we're doing X-ray spectroscopy, moving the origin about just as little as 0.025 angstrom could make the real and imaginary component of the transition moment change place. When it comes to the dipole approximation, we have that both of these expressions, the momentum operator explicitly is origin independent. For the dipole operator, if I shifted it, I would get a constant. But since the two states are orthogonal to each other, the contribution for this term would disappear. However, let me again re-emphasize that these values are not equivalent unless, of course, you're using exact wave functions and exact energy differences. And for some odd reason, we tend to like to use this guy, the dipole approximation, rather than the momentum representation. Finally, for the third term, I'm writing out an equation here that holds that if the momentum of mth order at the origin plus the displacement vector A is the contribution from all lower lying multiple moments at this particular position of origin. So here you sum up to order m. So that means that if m is larger than 0 and I move my origin, this transition moment would go to infinity as a goes to 0 if there's any lower lying moment that is non-zero. So that, for instance, an example I'm saying here that if I had a helium atom and I'm looking at the 1 to the 2p transition, which is only dipole allowed, if I start to shift the origin around, I could get it to be quadrupole allowed, etc., anything I like. One way away from this was demonstrated by Christoph Jacob and his student Bernadotte, which said one shouldn't use a Taylor expansion of the oscillator strengths where one did the transition moments to various order of the expansion, but rather one should look at the complete oscillator strength and do the expansion or the Taylor expansions in terms of the full oscillator strength. And if one do that, one will find out that each of these individual terms are origin independent, given that you use the same representation of the different components you're building it up. And here you might end up in a mess if you're mixing different gauges like velocity and momentum. So the sources of errors we're now going to look a bit into has to do with gauge mixes, where we're, for instance, using some components in a velocity representation, some components in a momentum representation. We will see that we will have errors due to truncations, and we will see that we will have errors due to that things are origin dependent, either because it is like that or because we have not fully achieved the origin independence that there should be. And also I'm saying that the errors are interlaced and strongly basis set dependent. So it's very hard to sort of figure out what's happening, and you might be tricked into that things are going fine. So here's a case of this molecule here, 2 irons and an oxygen in between. And here we're looking at a second order corrected oscillator strength. And we have sequence of curves here where we're just moving the origin along the line going through the oxygen. And we see here with small moves, let's say the red and the yellow one here, really not much is happening. We can also look here, this curve here, the black here, is the dipole approximation. And the orange curve here is the contribution from all the other terms if you do a second order expansion a la Bernoulli. And we see here the different peaks depends differently on these. And that's, we can also see the sort of the mixture of things that we can get curves that look very strange. Like here, we're getting, we have moved away 3 angstroms from the oxygen. We see that this curve separates, is different from the exact operator, which is the solid black curve here. So there are things that are sensitive. Looking at the truncation error, one might ask, do we converge to the right result from above, from below, or are we sort of having an oscillating trend? And for that particular reason, we're going to look at this molecular system here, iron with 4 chlorines around in a tetrahedric configuration. I'm going to go through the table here. So we're going to have dipole or 0th order contributions here, to the left in the length representation, to the right in the velocity representation. In the best of worlds, these numbers should be equivalent. We're going to have the second order term, and here I'm adding together both of them, so we have a second order Taylor expansion of the oscillator strengths. Here we have the numbers computed with exact operator. So let's start with this transition here, which is a dipole forbidden transition. And I'm doing this with 2 different basis sets. And we see here that things looks fairly balanced if I'm using velocity or length representation. If we're going down here to dipole allowed transition, we now see that very strange things are happening. If I, for instance, comparing these 2 different bases, I'm seeing that doing the second order expansion and truncating, the second order term actually gives me a negative oscillator strength, which is completely unphysical, whereas the exact value is a positive number. So this is really alarming. So just by doing the trick that Jacobs suggests, doesn't mean that you're off the hook. You can use a basis set where it seems like it's not a problem, but computation with another basis set gives you complete rubbish. We have also used this to look at this dipole forbidden transition, where we show that it's a quadrupole allowed transition, that the experimental results can now be completely reproduced by simulations. So let me just briefly summarize what we found out using the exact operator. It is now that we have an oscillator strength that is origin independent. We are assured that we're never going to have any non-physical values. And also we have an oscillator strength that is accurate for weakly or dipole forbidden transitions. So that gives us more information that we can reproduce from experiments. The bad thing is, for each transition, we will have to compute the nu of integrals to evaluate the transition moment. And that might be a problem if there are tons and tons of transitions to compute. As for instance, when you're doing X-ray spectroscopy, here we have thousands and thousands of transitions, and this might be a problem. But just let me briefly go through that. Here we have huge energy differences, and the difference between various transitions is not that huge. So yes, the energy difference between the states is used. The energy difference between the different states you excite from is not that. Could one use a representative K vector and use with the rest? So we have done some preliminary investigations, and then we said, well, let's do that. So here I have example, a molecular system, rather large number of basis sets. And here we can see the different spectra we get using the exact operator line in black, the red, where we use just one representative K vector. And here with blue is the dipole vector, and the green is the velocity operator. And the one that sticks out that is different is using the dipole operator. Apart from that, you really don't need to do the exact, but with a group, you get the exact, and it's almost at the same expense as doing the velocity integrals. So in doing this, we were able to reduce the time to doing the calculations from about 11 hours to 29 minutes. And we have very, very small deviations. So let me re-summarize here. So we have found that using the exact operator, you get very efficient way of computing oscillator strengths. It's accurate. It leaves you in a possibility now to also shine light on transitions that are weak and forbidden and compare those with those that are dipole allowed. Again, this formalism is now origin independent, and it's different from the truncated approaches. There's no reason to be worried that you will get unphysical results. And we also showed that in cases where you do X-ray spectroscopy, you don't need to do all those integrals over and over again. And this is a technology now that we would like to transfer over to ionization cross sections using dipole or Dyson orbitals. So with that, I would like to conclude. But before I take your questions, I would like to tell you that we have a position available here in Uppsala